Welcome to solverfy.
Problem 8.75. So you have these two blocks that have a spring compressed between them, and we're told what its spring constant is and how much it's been compressed. We're wanting to find first the accelerations of A and B right after the blocks are let go. Let's call that t equals 0 just for convenience. And then B, what are their speeds after they escape from the spring? So first, let's consider the conservation of momentum. Also notice that mb is equal to 3ma. That's going to be important. So since everything is at rest to begin with, there's no momentum. And so then at every point in time, regardless of whether it's during the spring expanding or after they've gone off 100 miles in either direction, doesn't matter. This relationship will always be true. And so for brevity, we can just call this m. And we know that this is 3m. So mva will always be equal to negative 3 mvb. So VA is going to always be negative 3 times VB. And this makes sense because this is 3 times heavier, so it should be going 3 times slower. Now, this is immediately useful for us because it allows us to do the next part pretty easily. This is true at all points in time. So if you take the time derivative of these, you'll find out that the acceleration of A is always in the opposite direction of and 3 times the acceleration of B. So if we only have to basically do each of these problems for A, say, and then we know what B is automatically if we divide by 3. Or do them for B and then multiply by 3 to get it for A. Either way. So right when the blocks are released, there's going to be a force of K delta L applied to each of them, and each of them are getting the full force because if this one weren't feeling a force that's equal and opposite to the one this is feeling, then the spring would be accelerating in one direction or another at the beginning of the problem, and we know that's not happening. So F equals ma. So then the acceleration of A is going to be K times delta L divided by M, which remember this is 1 kilogram. Excuse me. And this is 163 meters per second squared. Now immediately from this we know that the acceleration on B because it has 3 times the mass, but the same force is acting on it, is going to be 54 meters per second squared. So far, so good. Now, for part B, this turns into a conservation of energy problem. Our initial potential energy is 1/2 k delta L squared. This is equal to 1/2 ma, just calling m, VA final squared, which we'll just call V, plus 1/2 3m, so this is for this one. And we saw that the velocity of B is always going to be 1/3 that of A, so V over 3 squared. And if you do the combining in the algebra, we find that V, which is the velocity for A, is equal to the square root of 3k delta L squared divided by 4m. And now this is 5.23 meters per second. And because we know that 1/3 of that is going to be the final speed of B, we can just divide by 3, and we get that that is 1.74 meters per second.